Good day, ladies and gentlemen. Today we'll be focusing on the topic Newton's laws of motion, and particularly under this Newton's laws of motion, we'll be looking at Newton's second law of motion, and particularly under this Newton's second law of motion, we'll be now looking at an object that is pulled at an angle. And to look at this object that is pulled at an angle, we're going to look at this example. This example reads as follows. It says now a crate of mass 50 kg is pulled with a force of 100 newtons at an angle of 40 degrees to the horizontal on a rough surface. Then it further goes on to say the crate moves at a constant velocity. Right, ladies and gentlemen, this is the statement that we are giving. And from this statement, I can see that I am given a mass of 50 kg. I am given a force of 100 newton, and I am given now the angle of 40 degrees, and they have stated here that the surface is rough. I know you'll agree with me that when they say now the surface is rough, it means now friction is present. And then it says the crate moves at a constant velocity. And you know that when any object moves now with a constant velocity, there we know that our acceleration will be now equals to 0. Then, ladies and gentlemen, before we can attempt or try and solve this problem, we need now to draw a free body diagram. You know that a free body diagram shows me all the forces that are acting on the object, and I will draw now two free body diagrams. Before going to the questions, ladies and gentlemen, when you are faced with a problem of Newton's laws of motion, the easier way now is to draw a free body diagram. A free body diagram that is going to help you to identify all the forces that are acting on the object. And I will draw now two free body diagrams. I will first draw a free body diagram. A free body diagram without components. This free body diagram without components, ladies and gentlemen, it will look like this. I will have a dot there, and then from that dot I can see that my crate is on a surface there, meaning that there must now be a normal force, and then I must name this as Fn. Sometimes they use now capital letter N, and then this normal force, we know that because this object has mass, we know that there will be now a force of gravity represented by Fg, or now the weight force. And then as we can see, this object of mine, the applied force was applied now to the right, meaning now this object will move with a constant velocity moving to the right. So it says to me that my applied force will look exactly as the force that is applied at an angle. That is my force applied of I can say this is 100 Newton force, or now I can call it now the force applied. But then there's something that they told us here. They told us that this object is moving on a rough surface, and we said that when the surface is rough, friction is there. Friction is there, and we know that friction must oppose the motion. So friction will be there because this object is moving. We know that we are going to have now what we call the FK, which is the kinetic frictional force. Ladies and gentlemen, this is the free body diagram without components. Now, I will advise you when you are in an exam and then the examiner says draw a free body diagram of an object, I will advise you to draw a free body diagram without components. This, when the examiner asks you to draw a free body diagram in the exam, my advice is draw this free body diagram without components. But for yourself, in order to solve problems, you will then draw again a free body diagram with components. Free body diagram with components. But now, what are these components that we are talking about? The components we are talking about, ladies and gentlemen, is the components of the applied force. Remember, the applied force is now applied at an angle there. So it says to me that there's going to be a horizontal force that now moves this object to the right, and then there's going to be again a vertical force that will now tend to lift this object slightly off the ground. We're not saying this object is lifting the object upwards, but we are saying it just now moves it a little bit up. This will now be our vertical force, and then the free body diagram with components will look like this. I will then again have a dot there. I will make a big dot. So as to accommodate all my forces. Remember, the object is still now on the what? On the surface, meaning that I will have my normal force, and then I will also have now my vertical force. I can call it FV, or I can call it now FY. The choice is yours, ladies and gentlemen. So it then says to me, because I have a normal force, I will then have again my FG, or my weight force, and then still again I will have my frictional force. And then because I am drawing components of this force, I will not include this force. The first component we talked about is the FV, which is just says a vertical force, and the other one is now FY, which is now the other name they use. Instead of using FV, you can use now FY. The choice is yours. Then this force, it does not go alone. It goes now with a what? With a horizontal force. You can name it FH, for a horizontal force, or you can name it now the FX. Now these, the FX and the FY, these are the components of a what? The component of this applied force of ours. Now, ladies and gentlemen, with these free body diagrams, the one without components and the one with components, it then says to me that if I have drawn correctly these free body diagrams, then it will now assist me in solving the problems, ladies and gentlemen. Like I said, let's draw this free body diagram without components when the examiner says draw a free body diagram for a particular object. And then this free body diagram with components, let's draw it for ourselves so that we can see all the forces that are acting on this particular object. Because this one here, it does not show me that I have the vertical force, and then I also have now the horizontal force, which now we tend to miss in some instances. Now, with this free body diagram of mine drawn, ladies and gentlemen, I am now in a position of doing whatever calculation that the examiner can ask. Now, we can look at the question. A question can come to say, calculate the magnitude of the horizontal component sorry about the spelling there. Component of the applied force. You'll agree with me that the horizontal component, ladies and gentlemen, of the applied force, we are now talking about what? We are talking about Fx. And then you must always now remember this, ladies and gentlemen. Remember, this object of ours is pulled at an angle. And if the object is pulled at an angle, you know that when we apply our trigonometry, you know that from mathematics, if you then complete this, it's going to be now a right angle triangle. And then I am looking up for this force that is now horizontal. It means I'm looking for this Fx, and then you know that this side, which is now this Fx, is now going to be now adjacent to what? Adjacent to the angle. And then when it's adjacent to the angle, and then I have now this longest side, which is the hypotenuse. Ladies and gentlemen, you'll agree with me that for me to find the horizontal component, it's going to be Fx is equals to the applied force cos of theta. Cos of theta. We know that we get that from our trig ratios from mathematics, ladies and gentlemen. That is not a problem. Then I will have my applied force. My applied force of how much? Of 100 newtons. And then the angle. The angle is this one, ladies and gentlemen. The one that is between the horizontal and the applied force. And the angle, it was said to us, it was 40 degrees. And then it must now be 40 degrees. Then I will then put this into my calculator to say now 100 a cos of 40 will now give me how much? It will now give me 76,6044431. Therefore, my Fx, ladies and gentlemen, which is my horizontal component, will now be equals to 76,06 newtons. And then because this is a force, ladies and gentlemen, and we know that a force is a vector quantity, it has both magnitude and direction. I will then have to assign this a direction to say now this is going to the right. And we can clearly see that from our free body diagram that the head is pointing now to the right, meaning that this object of mine is moving to the right, ladies and gentlemen. And the examiner can further go on. The examiner can further go on, ladies and gentlemen, to say calculate. The examiner from this can further go on and say, let's calculate the magnitude of the vertical component of the applied force. The examiner can further go on and say, calculate the magnitude of the vertical component of the applied force. And then from our free body diagram, ladies and gentlemen, I know you'll agree with me that this is my vertical component. And from trigonometry, we know that Fy is equals to the applied force sine of theta. Then it says to me that my applied force still remains 100, and then my angle still remains to be now 40. Sorry for the mess, ladies and gentlemen. Then I will then find my applied force now to be now, when I insert this into the calculator, I will then find it to be 64,278,76097. And then in the exam, we know that the examiner will say round off to a minimum of 2 decimal places. Then this will be 2 to 8 newtons. And also, because this is a force, it's a force, it must have now a magnitude and direction. But where will I get the direction? I will get now my direction from the free body diagram. I can see now that my Fy, it's pointing upwards. Then I will then say it must now go upwards. Ladies and gentlemen, this was just now an easy marks to be collected in an exam. Then we can even go further to answer a few questions to say now calculate the magnitude of the normal force. Remember, ladies and gentlemen, in every calculation, I must now refer to my free body diagram. It says now, when I'm faced with this kind of a question that says calculate the magnitude of the normal force, they want now the normal force. I will then go to my free body diagram. My free body diagram with what? With components. To say, where do I find this normal force? You'll agree with me that my normal force will now be found on the vertical. Then it says to me that where I find my normal force, I find my normal force on the vertical. And then how many forces are acting on the vertical? I have the normal force, I have now the Fy or the F vertical, which is a component of the applied force, and then I also now have the Fg, ladies and gentlemen. But we know that this object of mine is not moving up or down, but it is only moving where? It is only moving horizontal horizontally to the right. So it says to me, the sum of the forces in now in the vertical plane must now be equals to 0. But how do they equals to 0? Because this object of mine is not moving vertical, it is only moving now in the horizontal. So it says to me, when I add the sum of the forces, the net forces in the y plane or in the y direction must be equals to 0, ladies and gentlemen. Why do I say that? Because the object is only moving horizontally, it's not moving vertical. So the sum of the forces in the y direction must be equals to 0. And we can see that from our free body diagram. I have the normal force and the vertical force that is now acting upwards, and then I have Fg that is now acting downwards. So it says to me, I must now choose my direction to say now, let all the forces, because now a force is a vector quantity, it has magnitude and direction, ladies and gentlemen. I must now choose the positive direction and the negative direction to say now, let these forces that are going upwards, to be positive, and the forces that are going downwards to be negative. Ladies and gentlemen, you'll agree with me that you were taught this. Now, because now this net force or the resultant force in the x is equals to 0, it says to me, when I add these forces, they must now be equals to 0. But how do I add those? I will add them in the following manner. To say, I have the normal force and the Fy which are going up, and then they must be positive. To say, let the normal force plus the Fy plus, ladies and gentlemen, because it's net means the sum. So I will say now plus negative Fg, and then all this must now be equals to 0, ladies and gentlemen. But the examiner, this is a very, very important statement. This statement is the one that's going to allow me to find the magnitude of the normal force. And then if I'm there now, I can now make the normal force the subject of the formula to say normal force is equals to, let me transpose this Fg. Fg was negative this side, and then when I take it to the other side, it's going to be positive. I know, ladies and gentlemen, you know that from mathematics. And then let's look at this Fy. Fy is positive on this side, and then when I transpose it to the other side, you will agree with me that Fy will now be negative. So with this now equation of mine, I will now be able to find the normal force. So normal force for an object that is being pulled at an angle, ladies and gentlemen, your normal force will be equals to the Fg minus the Fy. And then we can further now break this Fg. We know that Fg is a weight force, and weight force equals to what? Equals to mg, which is just the mass multiplied by the gravitational acceleration. And then we know that our y component, as we have already solved for it, we know that the Fy is equals to the applied force sine of theta. Ladies and gentlemen, I am repeating this so that you can be able to grasp this, that the y component is equals to the FA sine of theta, like we did here in the previous equation, to say our y component is equals to the FA sine of theta. Then if I am in this position, I'm now able to calculate for the normal force. To say, we know that the mass from our question here, the mass was given to be 50 kg. The mass was 50 kg minus, I know that the F applied was 100. Ladies and gentlemen, we forgot now to put the gravitational acceleration. Let me squeeze it here to say now the gravitational acceleration must now be 9,8. Or let me rather do this. My mass was 50 kg, and then my gravitational acceleration is 9,8. Please, ladies and gentlemen, don't do the mistake that I just did now. So we are fine with this. It's the mass multiplied by the gravitational acceleration, and then minus the F applied. F applied is now 100 newtons. But now, because we are looking at the vertical component, we must now include the sine of 40 degrees, and then this will now give me the magnitude of the normal force. Remember, when I insert this, it will now be 50 multiplied by 9,8, and then I must subtract now the sine of 40, and then this now gives me a magnitude of a normal force of 425,721239. Therefore, my normal force will now be equals to 425,72 newtons. But normal force, remember, it's still a force, meaning that it has both magnitude and direction. And from my free body diagram, I can see that my normal force is acting upwards. Then I will say now upwards. Ladies and gentlemen, I hope now we are clear with that part. Then we can now even go further to another question. Another question can say now to us, calculate the frictional force. Calculate the frictional let's say the frictional force. Frictional force. Calculate the frictional force, ladies and gentlemen. Right now, our frictional force, for us to calculate our frictional force, ladies and gentlemen, we know that this crate of mine moves at a constant velocity, and we know that if they say an object moves at a constant velocity, you'll agree with me that the acceleration is equals to 2 meters per second. Acceleration is equals to 0 meters per second. And then for me to calculate the frictional force, I must then look at my free body diagram. And then in my free body diagram, I can see now the frictional force. I find it now in the horizontal plane, meaning that when I want to calculate the frictional force, I must now look at what? Look at the forces that are on the horizontal. And then those forces are frictional force and then Fx. Ladies and gentlemen, to calculate the frictional force, you'll agree with me that I must now look at the forces F net in the x direction is equals to ma. We know that we get this statement from Newton's second law of motion. So we know that this object moves at a constant velocity, meaning that its acceleration is equals to 0. So you'll agree with me when I say now also my net force in the x direction is equals to 0. I hope you'll agree with me, because when I take the mass which was 50 kg, and then I multiply that mass by 0, you'll agree with me that I will also now get 0. And then it says, let me define F net, meaning let me break now this F net into the forces that are acting now in the horizontal. And then from this free body diagram of mine, I must then choose my direction. For me to choose my direction, I like now to choose the direction where the object is going. I like to choose that direction to be positive, and then this direction now to be negative. Then it then says to me my Fx, ladies and gentlemen, it must be positive, and then because it's net, I will add, and then I will get now a negative Fk is equals to 0. And then they said now I must look for this. So it says to me that when I make Fk the subject, it says to me that Fx will be equals to Fk. So ladies and gentlemen, I hope we are clear on that if this object is moving at a constant velocity, its acceleration will be equals to 0. And then if the acceleration is equals to 0, ladies and gentlemen, we know that this mass multiplied by gravitational acceleration will give me 0. And then in that case, it then says to me my Fk will be equals to my Fx. So we have already found Fx in the previous example, to say Fx is equals to 76,60, meaning that Fk will also now be equals to 76,60 newtons. But remember, Fx was going to the right, but frictional force from our free body diagram, we can see that it's going to the left. So I will then include the direction to see it's now going to the left, ladies and gentlemen. And then let's now look at the last question. The last question can say now which is just a simple question, and usually these questions are asked at the end of the question. We'll then say now let's take this to be now a question number 5. Question number 5 will then be now it then says will the coefficient of kinetic friction change if the angle of the applied force is decreased. My spelling, decreased. Right? Yes or no? And then it then says to us, give reason. Give a reason for your answer. Ladies and gentlemen, we want to know whether the coefficient of kinetic friction will change if the angle of the applied is decreased. What do they mean by that? We want to know whether the coefficient of kinetic friction will be affected if this angle is decreased, maybe is decreased to 40 degrees. Then I know you'll agree with me that this coefficient of frictional force will not change. So my answer will be no. And then they say we must give a reason for that. So if I want to give a reason for that, you know that the coefficient of friction, I will say friction to include static friction and a kinetic frictional force. You know that the coefficient of friction is only dependent on the type of surface, or on the type of material between the two surfaces. The frictional force, the coefficient of frictional force only now depends on the type of material, or we can say now, or on the nature of the surface. Ladies and gentlemen, what are we trying to say here? What we are saying is that the coefficient of friction only depends now on the type of material, or now the nature of the surface. Remember, when we apply a force, this coefficient of ours does not depend on the amount of the applied force, but it depends on what? It depends on the type of material, or now the nature of the surface. Ladies and gentlemen, with this being said, we'll stop here for today. And if you like the video, please subscribe to the channel. The channel is Tlotlanang Matsididi. And then if you like this video, please share it now with your learners, with your classmates, and all those. Ladies and gentlemen, with that being said, thank you very much for watching. I will then post a follow-up video on this Newton second law. The aim is to now create a series of videos of each and every concept, or each and every topic on physical sciences. We are just starting, ladies and gentlemen. We've started with grade 12. We are now on grade 11. We'll also now be doing the grade 10 videos on physical sciences. Thank you very much, ladies and gentlemen.